Welcome to Gradcast, the official podcast of the Society of Graduate Students at the University of Western Ontario.
Hello everybody and welcome to Gradcast, the official radio show of the Society of Graduate Students here at Western University in London, Ontario. I'm your host, Alex Moszczynski, and today I'm joined by co-host Adrienne Borrie. How are you today?
I'm great. How are you doing?
Pretty good. I'm excited. This is our first time, I think, hosting a live episode together. We did a podcast once or twice together, but we've never hosted with you, so it's a pleasure to work with you.
Oh, well, thank you.
Anyway, how have you been?
Pretty great. I'm excited to talk to our guest today and about stars.
All right. Well, let's jump right into it. Parshati Patel is a PhD student here at Western University studying physics and astronomy. Welcome to the show.
Thank you for having me.
Thanks for coming. You approached us, actually, to come on the show, if I'm correct. Never mind. Tristan found her. Darn it. All right. First fact wrong. Anyway, so you're originally from India.
Yeah.
And you moved to Canada in 2010. 2006. Darn it, 2006. Second fact wrong. You got your undergrad from the University of Toronto in 2010.
You know that actually if he gets a third fact wrong, your interview's free.
Oh, okay.
It's true.
Well, okay.
Okay. So you did your undergrad at U of T. How did you like Toronto compared to India, and how did you find University of Toronto?
So it was very different for me because I come from, comparatively a smaller town in India, and so it was a big city life that I got to see, which is really cool. I'm pretty excited about studying astronomy. Didn't really get into anything else until I finished it. But yeah, it was fun.
That's good. I did my undergrad at U of T as well, but I was born and raised in Toronto, so Toronto was home to me and still is, I guess. So what was the transition from Toronto to London like for you when you came to Western?
So when I first came to Western, because I had lived for 4 years in Toronto, it was a little bit different because it was like going back to the old small town life, which I now like it here. Initially I was not happy about moving because I was like, oh, I'm going to move from a big city to a smaller city. However, Western was excellent at accommodating, especially being an international student. It's a transition that takes years to kind of get into the, rhythm of everything that goes on here. So I'm fine now here.
That's great. So what was it like to be an international student in a new place, studying physics and astronomy, and kind of how did you get into that area of study? So
actually, my parents took me to a planetarium on one of our vacations, and I used to always ask questions. My parents would always refer me to books. So they finally took me to planetarium. I got hooked at looking, the stars and how they form, the planets, and the universe, basically. I got to look through the telescope for the first time there. And then basically I was hooked. I thought, to study something that is bigger than what we see here on Earth is just, that's a dream, one would have, to actually go to space or actually study space. And so from there, I just decided I wanted to study something related to space. And so I decided that I need to go away from India to kind of, concentrate on what I want to do. So I came to Canada in 2006 with a dream to study astronomy and do a PhD in astronomy. And I think I'm on the right track now.
Well, that's amazing. So you're studying with Dr. Sigat and Dr. Landstreet, is that correct?
Yeah.
So Dr. Landstreet studies the stars. Is that what I'm...
Yeah, he studies stars. He actually studies magnetic fields. That is his expertise. And so, land, Earth, magnetic fields, it's all related.
It all ties together. All right. So specifically what you're studying is the formation of stars, of a very specific class of stars. What do we mean when we're talking about different classes of stars? Like, I look up in the sky, they all look like little tiny dots to me. How do we differentiate them?
So just with your naked eye, you can basically differentiate stars with their colors. Okay, so you sometimes, especially if you look through a small telescope, you see stars either red or blue or white. And basically the color of the stars tells you the temperature of the star. Okay, which is very important because our sun, which is, as we see, yellowish orange, is around 6,000. Okay, so that, it sounds very high. 6,000 degrees is a very, very high temperature. But in terms of stars, you can get anywhere from 3,000 to 40, 50, 60,000. And that's the temperature of the surface. Okay, wow. So they can get really, really hot. And so depending on how hot they are, how their life moves on is different. So that's why there's different classes where you study sun-like stars, which take a longer time, spend long time on every phase of their life, whether they're baby or adult star or old age. But stars that I study, which are called her big stars, their temperature ranges anywhere from 10,000 to 30,000 on the surface. And so because the temperature is so high, they evolve really, really fast. And so the reason why we like to study these stars is because they evolve really fast, and so we don't get to see as many as you would see a sun-like star. So that's the whole reason.
So by really fast, like what's our time scale here? Is it like 5 years and it's gone, or
no.
5 million years, or billions?
So for a star like our sun, it's in billions of years. Like our sun right now, it is what we'll call an adult age, and it's going to be in this phase where it's burning hydrogen, converting into helium for next at least 4.5 billion years. But stars that I study are in fast-tracking things in millions of years or 100,000 years.
Oh, wow.
Which is way faster when you compare it to the stars that we live around, like our sun, or the stars that we think we would find planets around, which are like sun-like stars. Because they are there for a longer time, you'd expect planets or maybe life around them.
So the question about these stars, sorry, Adrienne, so does that affect their size at all? Like, are they, like, I imagine that the timeline is from when they start fusing until whenever. Mm-hmm. So are they a certain size, and that means that they must die in a specific way too?
Yeah. So one thing I didn't mention before is the temperature. The more the massive the star is, the more the temperature. So the stars that I study are also massive, in addition to being really, really hot. Okay, so they have more material to kind of burn from hydrogen to helium, but they also have very high temperature, so they're going to convert things really fast as well. Okay, so our sun-like star, assume our sun is 1 solar mass. These stars are, 10 to 20 solar masses, so 10 to 20 times the size of our sun, mass of our sun. So they're pretty big, and so their life, that's why it goes way faster than stars like our sun does.
That's so interesting. So one thing that popped into my head was, if these stars are burning really big and really fast, does this make them less conducive to having life around them? Because, my sort of understanding of life evolving, it takes millions of years. So if they're burning out in 100,000 years, then these stars don't have as good a chance of having life around them?
Yeah, so that's true. That's the whole reason when they're looking for life around, or looking for planets that would be habitable planets, as they say, like our Earth, they actually look around stars that are sun-like or smaller in size.
Oh, cool.
Because they would have longer time to, get rid of all the gas and dust and just leave behind planets, which, if they're in the right place in the solar system, would have life. So that's why we look at those sun-like stars to actually look for life. But stars that I study are more massive and they evolve really fast, so you would practically not expect life around them, because they do have stars, they do have planets around them, but they are still very young to actually host life around them. So
these Herbig stars, right?
Yeah.
Okay, so I know that stars have lots of really cool ways that they die. And if these ones are really big, does that mean we expect some sort of nova or maybe some sort of singularity at the end of these things, or no?
Yeah, so black holes, probably because these stars are very massive. So massive stars make black hole, and little bit less massive make supernovae, so we would expect them to go supernovae, leave behind a neutron star, or be a black hole. And so it won't be as magnificent for our sun, but for these stars, it is brilliant to look at.
So you might say the Herbig stars live fast and die young.
Yeah, actually, all the other phases in their life are really sped up compared to our sun. So that's the whole reason why we'd like to study them, because, you know, for stars like our sun, things are stagnant. For example, we see the solar system right now, but we don't know what came before that. Okay, so we look at stars which are still younger than our sun, but also look at stars which are way more massive, but still in that phase where sun would have been once. Okay, so we are basically looking for the past, or our past, basically, and trying to use these stars to even understand how they form, because, you know, small star forms differently compared to the massive stars, and that can tell you whether you're going to find life or not, or planets or not. So.
But if the trajectory of the life of these stars is so sped up, and the actual sequence of events might be happening a little bit differently, how similar is it to our own sun, and how much can we extrapolate without missing certain things or possibly making too many comparisons?
So these massive stars, internally they're different in a way that the way they burn or transport energy is different compared to the stars like our sun. So their trajectory still looks the same, where, you know, they go from a massive cloud of gas and dust to these objects that are creating all these matter onto them. The more matter creating, the higher the temperature, and basically from there shrinking to a smaller size, which our sun did at its point in baby phase as well, and sinking on to what we call the main sequence phase, or the adult phase. But the time span, or you would say the trajectory that it takes, is just sped up. It's exactly the same thing, just for more massive star. It's just more sped up. Yeah.
Okay. So what? So you said the Herbig star. I can't remember if you said it already or not. What kind of star is our sun? What would its class be?
It's a G-type star, and Herbig stars are B stars. Now, initially when the stars were named, they were named A, B, C, and then they eliminated the ones that, you know, were mostly in the other classes. They could fit in the other classes, and then obviously they were switched around based on how much hydrogen you can see in the spectrum. So O comes first, so those are the most massive stars. B comes second. A, G.
Electronic device you're going through right?
Yes. Oh, be a fine girl, kiss me. That's the way you remember. So G is just a couple before the most smallest one you can find, and so they are not the most common ones, but they are the ones that you would find life around the most. Yeah.
So when you're going about studying these stars, how do you pick a star to study? Do you kind of just like sit down and look up in the sky and say, "That's my guy"? I'm going to
second one to the right in the morning.
Like, yeah, how do you select a star?
So initially when I started this project, my supervisor already had a huge data set where I could pick these stars, and other people have already done work to say, oh, this is a Herbig B stars, or oh, this is a Herbig AE star. So they already had this catalog made. So I basically picked from there, but I did get a chance to actually do an observing proposal where I could actually pick the stars I like. So basically I go through this whole catalog of, you know, where the telescope is located and what latitudes can look at and what stars I could pick. So I actually got to pick the stars I wanted, but it's basically, you know, which one is probable at this time of the year from where the telescope is situated. That's basically it.
Okay. Yeah. And the way they studied them, like, forever, like, I remember being told that, like, the first people to classify stars were literally, like, just these room full of, like, middle-aged women just looking at these like, glass sheets and, like, identifying, like, this is this type of star. And that's literally how they built the first catalog of a lot of the major stars.
Yeah, and that's why they had to eliminate a lot of these, right? Because they cataloged it to A, B, C, and then they realized that some of them were actually subclasses. And so a lot of the C's and things are gone from the categories now.
So maybe we should move into the research on planetary formation.
Yeah, so what can you tell us about the formation of her big B stars?
So the way I study the formation of these stars is I study the disks around them. So these disks are inherited by this star when they're in the star formation phase. Basically, these stars have almost just stopped accreting. So they still have this large reservoir of dust and gas around them, which basically forms a disk, and there can be different kinds of disks depending on what you want to study. So closer to the star, you would have a gaseous region because the temperatures are so high, the dust is going to evaporate. And then further away, you would have cooler regions where you would start sealing molecules, and then dust, which will, start settling down depending on time, and you'll start getting these pebbles to giant planets. So depending on what area you want to study, you look at the disk. So I look at the disk very, very close to the star. And the reason for that is these stars, you cannot actually see the star, okay, because they are covered by this thick wall of dust around them. So the way we want to study how they form, or the way they're accreting, is by studying this area of the disk. And generally in stars like our sun, they have large magnetic fields. And so they basically accrete all the material through the magnetic fields. But less than 10% of these stars we have detected magnetic fields around them. So which means that they don't have magnetic fields, but they're still accreting material. So how are they doing it?
So these are stars not emitting magnetic fields. I mean, they're not spinning? Or? Well,
they're spinning, but they have very, very small convective core. Convection is what drives magnetism. Okay, so they have very, very small magnetic core which cannot produce large enough magnetic fields that covers the whole star, or they have a completely radiative core, which means things are just transported with all these photons that are coming out, and that cannot generate a magnetic field either. So you need some kind of convection going on to actually generate these magnetic fields. So theoretically they don't have magnetic fields. We have only found less than 10% of those. So we think there's an alternative explanation of how these stars accrete material onto them. And that is what I'm testing, is how do these material go from the disk onto the star? We think that happens in the equatorial plane of the disk, as you say, which goes directly onto the star. Now, that is what we call classical accretion. And so we are testing this theory by studying the gaseous region of the disk.
How many of these disks does an average star tend to have? You mentioned the one closest to the star. Does that mean that there's multiple concentric rings that come outward from the star, or a few?
No, so it's not concentric rings, but it's more like a flowing disk. It's the people who actually study them tend to differ them that way, differentiate them that way, because, for example, I'm someone who studies gaseous disks, so I don't really care what happens, anything beyond that point. Or people who study molecules don't really care about, the gaseous region that I'm studying. So they kind of have these areas of expertise that people try to dive in. But that's the only reason we can differentiate the disk, is if you look at molecules and atoms and dust and things like that.
So it's kind of like one disk, but along the way it's made up of different things, so you kind of stratify it based on what it's made of.
Yeah, and that's all because of the temperature difference that would happen from the star to the cold interstellar medium, as we would say, the space.
Okay.
A kind of question about looking behind the curtain here then. So then what is an average day of an astronomer doing research then? Because it's not it's kind of more akin to history and paleontology than hard natural science, because you can't do experiments. How do you? Is it I don't know. I'm just gonna ask.
So I'm doing a combination of observational astronomy and a computational astronomy. So my supervisor has a code which can generate a star and a disk around it, and so from that we interpret what kind of spectra we get, or how much energy will come out of this disk if you shine this much amount of light from the star, and we compare that to our observations that we already have. So it's basically me using the codes, generating the kinds of stars that I have, the amount of, based on its size, temperature, mass, different sizes of disk. Since we cannot...
simulation?
Yeah, it's a simulation. So we cannot really see this disk or the star, the central star, so we have to kind of guess. So no one has actually worked in this region in terms of gaseous disks. And so for me, it's a starting point to start with what size of disk you would expect and what it would be made up of and how you would expect the same kind of observations as, you see in the observations. So that's basically my day, running simulations, comparing it to the observed data, and then interpreting how much of it actually makes sense in terms of physics.
And how do you get the observed data? Do you look through a microscope? Do you have a special type of machine that you would look through the microscope with that's going to measure it somehow? Like, how do you get information on the rings that surround the star to find out what they're made up of?
So we actually use the Canadian France Hawaii telescope, Canada-France Hawaii telescope in Hawaii, to actually get spectrum of the star. So basically it's the visible light, like the rainbow that you see. We basically take that onto a computer, analyze, we know what lines to expect in terms of, hydrogen is going to be at this wavelength or carbon is going to be at this wavelength. So we look at the whole spectra, try to determine what kind of, material is it made up of, what kind of elements does it have. And so the way we do it is basically point the telescope to the star. And luckily it's being done by the people who are there. You don't now get to go to Hawaii, but yeah.
If I remember from what I remember, I could be wrong on this, but universities have to fight to rent space on these things.
Yeah, it's actually, that's the observing proposal that I was talking about. You actually fight for time. So you have to fight for time with other people who are applying. And so basically when you are fighting for the time, if you get it, then they point the telescope for you to the place you want, and then 24 hours later, they send you the data they have collected. So yeah, it's basically them doing the work, me getting it. So, and analyzing it on a computer.
Just gonna put the space in your Dropbox.
That's actually how they do it. They email it to you.
So if we're looking from the ground, does that mean that atmospheric conditions can ever affect your results? Like what happens on a given day when there's more smog? Yeah, so it actually very much depends on the weather. So when they tell us they're going to do this observations, it can be done anywhere in span of 4 months, and you basically get email after 24 hours because they only try to schedule you in for a time-sensitive event. But to just get a spectra of a star, they can do it any time when the weather is good. So if the weather is not good, I don't get my data. But at least 1 day in 4 months would be good enough to get my data. So yeah, it's very much weather dependent.
And once you have this data, what do you need specialized software to analyze it? What sort of programs are you working with?
So we are actually using a couple of different programs. IRAF, which is actually specialized for astronomers, where you actually analyze these data that actually come out of the telescope, and then you use softwares like MATLAB or any plotting software, Python, to actually plot these up. And then the simulations that I run are codes by my supervisor, which are in Fortran. So there are a lot of different softwares that we actually use, but basically IRAF, MATLAB, and Fortran is what we use right now.
Why do they choose to put the telescope, I was going to say microscope because that's what I work with, the telescope in Hawaii? Is it just a clear picture of the sky there? People just hanging out in Hawaii? Why Hawaii, and what would be the best place in the world that you can think of to have a telescope that would give you the clearest view? So there are a couple of different reasons why they put it up in Hawaii, and yet the places like in Atacama Desert or in other places like Lake Ladakh, India, is because it's A, high up, B, the air is dry.
you don't want, your telescope condensing out or things. And you want a clear weather most of the nights. So places like Hawaii, right on the summit, you hardly have any days where you have, snow or a lot of clouds. So the best chance is to do it from there than anywhere like Toronto, or it's also technically away from big cities. So that is another thing, you want to avoid the light pollution as well.
That's so great. So just sort of switching gears a little bit towards the end of the interview. So your website mentions that you like to participate in outreach efforts. Could you tell us a little bit about these before you go?
Yes, I've been involved in a lot of different things for the past couple of years. I've been part of teaching assistantship to kind of do outreach activities with school kids or even public, basically, showing them the wonders of science, I would say. I also have to work at the observatory right here on campus, and basically have people come in and look at the stars through the telescope. And I also produce a podcast called Western Worlds, which is produced by Center for Planetary Science and Explorations, which basically talks all about space. So you guys can tune in starting mid-September. We are launching our new season, so you can tune in at cpsx.uw.ca/Western Worlds.
Awesome. That's amazing. So in terms of this outreach, does that mean that I can go check out the planetarium, or is it only open to,
So
kids?
at the telescope, so the observatory is open, at least in the summer it was open every Saturday,
Okay.
8:30 to 11. From September to April, it's once a month because it's cold. But it's still once a month. It's free parking, and it's 7 to 9 p.m. And anyone can drop in. It's free of charge. Bring in kids and people who are interested.
Yeah, that's amazing, because actually my lab mate went there on the weekend and was telling me that you can see some of the planets up close and personal, and she was saying that you can see some of the rings around Saturn, and that's awesome. So will you be there?
I work most of the time. I do. I'm not sure if I'm going to be working next semester, but I'm sure some of my friends should be able to show you the rings of Saturn, but also deep sky objects if you are there on a clear, dark night.
That's amazing. Well, I think that's all the time we have for the show today, so thank you so much for coming.
Thank you for having me.
All about astronomy. Thanks, everybody, for listening. This has been Gradcast. See you all next week.
That's all for this week. If you want to send us some feedback, or if you want to come on the show yourself, email us at gradcastradio@gmail.com. Be sure to hook us up on social media. On Twitter, we're at GradcastRadio, and look up Gradcast Radio also on Facebook. If you want to subscribe to the podcast is located at gradcast.podbean.com, and it's on iTunes. And while you're there, why don't you leave us a review? It really helps us out. We'll see you guys next week.